Okay, in this video I want to talk about several ways that Newton's method can fail to work. We hope that it helps us to get a good approximation of a root of some equation, but it doesn't always. Now, what I've done here is I've written down the formula that we derived in the last video so that if we want to work with things algebraically, we can. And I've also drawn an example on the board of just the cube root function, or x to the 1/3. Now, I have to admit, this would be a silly function to use Newton's method for, because I can tell exactly where this is going to equal 0. This is going to equal 0 at 0. So my familiarity with that function, I know exactly where this is 0. But let's just suppose we were trying to look for this x-intercept using Newton's method. This is a great illustration of how Newton's method can fail using a familiar function. And there could be other functions where the root is a little less obvious, but they have the same issue. Let's just suppose I made an initial guess of x1. So I know I'm going to follow the tangent line to get to my next guess. And if I do that, I'd intersect the x-axis right around here. Looks like about x2. That looks like that's farther away from 0 than x1 was. And then I'd do that again. So I'd come to this point, and I'd follow this tangent line until I'd hit x3. That looks like it's even farther away than x2. So instead of my points getting closer to the root, they're getting farther and farther away. Now, in this case, we can sort of see why that's the case. Notice that x cubed, and I didn't draw a perfect graph, but I did try to capture, it's got a vertical asymptote at 0. Because if I were to take a look at f prime of x, I know that's 1/3 x to the -2/3, or 1 over 3 times the cube root of x squared. Okay. Now at 0, that's undefined, and the closer we get to 0, the bigger that gets. So we've got a vertical tangent here. So the problem is, the further away I am from 0, the less steep the tangent line is. So that's taking me further and further away from my point instead of closer to it. So in general, if I have a situation like this, where my function isn't differentiable at a point, particularly if there's a vertical tangent at that point, Newton's method is probably going to fail. Okay. If I were to use this formula on this function, notice that I would get x sub n plus 1, my next guess, would be x sub n, my previous guess, minus the function f was the cube root function, so that would be xn to the 1/3. We said f prime was 1/3 xn to the -2/3. That's just evaluating it at x sub n. Now notice, that's x sub n minus, let's see, x sub n to the 1/3. Sorry. I'm going to bring up that negative exponent. So that's going to give me x sub n to the 3/3, which is just x sub n divided by 1/3. But that's x sub n minus 3 x sub n. That's -2 x sub n. So what we saw geometrically with the fact that it looked like we were getting further away, we can actually now see algebraically. Obviously, the sign of x sub n plus 1 is going to be the opposite of the sign of x sub n. So we're bouncing back and forth between the left side and the right side of my graph. But the absolute value is doubling each time. So we're getting twice as far away as we were in our previous guess. So this is definitely not working. Okay, so that's one way that Newton's method can fail. Now, if you recognize that you had a vertical tangent, you could say, oh, better not try Newton's method. Okay. If you just started using Newton's method and you did it a couple times, you would notice that your numbers weren't getting closer and closer and closer to some number. They seemed to be spreading apart, and that would be a sign that it probably wasn't working. Now, that's not the only way that Newton's method could fail. Another way would be if I had some function And near my 0, there's a place where I have a horizontal tangent. Notice, if I were to guess at some point this location where I've got a horizontal tangent, well, I can follow the horizontal tangent forever. I'm never going to intersect the x-axis. Algebraically, that would be reflected by the fact that the slope of that tangent line is 0, and so this formula for my next guess is undefined. So that's another way that if you end up with that guess, it's going to go wrong. Now, sometimes you can deal with this situation by just adjusting your guess so that you can avoid that point. Okay. Other things that can sometimes happen is sometimes a function is going to have 2 roots, and sometimes they're kind of close together, and sometimes one guess, the tangent line approaches one of those roots, and then the tangent line at that point approaches the other one, so you're sort of bouncing back and forth between 2 roots. So there are lots of different things that can go wrong with Newton's method. And basically, you try it. If it looks like the numbers are converging to some number, then that's a good evidence that it's probably working. And if it looks like they're not, like they're bouncing back and forth, or like they're just getting further and further away from each other, then that's a good sign that it's probably not working. Now, there are some theorems about when it will work and when it won't work. This is sort of a standalone section, so I don't want to go into too much detail. I just want you to be aware that it's a great method much of the time, but it's not guaranteed to work all of the time. Okay, and this is a fairly short section. You'll notice I didn't assign a whole lot of homework, and just a reminder, depending on what technology you have easy access to, reinterpret the directions on the homework if necessary. I do want you to practice using Newton's method. I would recommend that you practice doing the first iteration by hand, and then if you have a programmable calculator or some computer program, if you know how to use Excel, that works so that you can do multiple iterations without having to punch each one in individually, then go ahead and do Newton's method multiple times. If you don't have access to that technology, I am not expecting you to, by hand, or even with a calculator where you have to individually punch things in, do this 20 times in order to get a really accurate estimate. I want you to understand the basic process and the theory behind it. That's what's most important.